Well, we're nearly there. Welcome back, everyone. And it's official. Spring break has ended. I hope you had a restful break. Me personally, it was more just battling, what's that word? I used to know that word. I must be tired today. There's a lot of battling procrastination, but I eventually got through it. I hope it wasn't as bad for you on the procrastination front. But now we're in week 11. This is kind of the more pivotal week that we're getting in through for the course. On week 11, we take a look at the syllabus, there's really not a whole lot left. We are right here, 31st of March. We will have 3 instructional weeks. We'll do an exam week, then 1 more instructional week. Then this is closed week, so we won't have any new material we'll be reviewing at that point. So that means we're nearly there. There's still exam 3 and the final exam on the table. So that means there is still, looks like 40% of the course up for grabs just in terms of exams. Lots of stuff going on, and that means weeks 11 through 14, 15, and 16 are going to have the strongest impact on your overall grade, not just in this class, but really all of your classes. It's kind of unfortunate that we had a huge break. We fall off our normal routines of getting through the work, and now we have to just start up right back in week 11, working harder than normal to finish off the course. It is a little bit rough, but we'll get through it. The light will be there at the end of the tunnel once we're out there in May. But welcome back, everyone. Before we get started with the material we left off on section 5.3, any questions or comments whatsoever? Okay, well, let's get, oh, sorry, comment over here. Gotcha, sorry. Okay, let's get started then, folks. So we were on example 3 in section 5.3. But it's been a while. Induction's not easy, and strong induction is a more abstract feeling kind of a technique. So here's example 2. I feel like we should just take a quick look at this before we just launch into a brand new problem. So what we were doing in example 2 was we're dealing with a recursively defined infinite sequence. So we know the values of the first starting terms. A1 initially is 3, A2 is initialized to the value 5. But once we have these 2 initial values, we recursively define the value of the sequence, an, for all values greater than or equal to 3, using these values. We'll say, for doing, say, A3, in fact, just for the sake of review, let's do A3, just to see what we're doing here, kind of knock the dust off our bit of a break that we had. Using this part right here, we go to calculate A3. I must be rusty with that red dot. It wants to go where it wants to go. A3 would be equal to 3 times A2 minus 2 times A1 is what this would be saying here. So then we just use the prior information and say A3 is 3 times, A2 is this one, 5, so we have to put things in the right order. It's kind of defined in a strange way. A1 is this value, 3. So we get that A3 is 15 minus 6 for a value of 9 altogether. And using this structure right here, we can generate more and more terms, as many as we would like. In fact, that's essentially what we did with this. We took it way down the bottom here, we implemented that same structure right there through the pseudocode, and we tried running it through a couple examples. We tried running this at n equals 330, something like that, and we realized very soon this was not going to terminate, not the end of class, probably not for quite some time, really. That's where method 1 started to shine. We could calculate the value of any sequence extremely rapidly with just this structure, but we would have had to know that 2 power of n plus 1 actually gives us all of the terms of this original sequence right here, defined recursively. So that's what example 2 was really all about. We took all of this information, and someone supplied us with the formula. They said, we believe for all integers n greater than or equal to 1, this is going to give you the value for all terms of this recursively defined sequence. And if you're right to be suspicious, really in our base case right here, we say if n is 1, a1 is 3, then we use that formula and double check if n is 1 in that formula, did we really get 3 out? That's us being suspicious. I mean, that's how the proof by induction should start, whether it's induction or strong induction. But for strong induction, we need to check out one more case, see if this comes out as true, that we get 5, plug in the formula, and we really did. So now we were well on our way. So any questions at all, folks? Just refreshing on how the base case goes for induction. Okay, this took us then to the inductive step. Let me zoom out just a tad. In the inductive step, we're on step 2 right here. Here's the definition of proof by induction, strong induction specifically. And notice what we assume in the inductive hypothesis. We assume a lot. If we checked out case n is 2, we go up to one higher integer, say n is greater than or equal to 3, and assume this one starts at p0, but r started at p1, p2, all the way up to this case, pn minus 2, pn minus 1, are all true, meaning the formula here is going to generate the right terms of the sequence all the way to a1, a2, a3, and an minus 1. All we have to do now is show that this implies Pn is true directly, using the assumptions to the left. So this is a pretty big logical structure. Notice it's stringed together by ands. Also, it's an implication. So assuming the truth of this, showing Pn holds, will complete the entire proof. So we made the assumption. This is just another way to say that assumption there if you want to make it compact. Here's us saying that we want to show Pn is true, specifically an comes out this way. And once we wrote out an, it's 3 times an minus 1, but an minus 1 is captured here, the predicate function of Pn minus 1. We assumed it's true in the inductive hypothesis, but that's just a statement that the n minus 1 term of the sequence is gotten through the formula to the power n minus 1 plus 1. So we dropped it in here. Likewise, we made the same substitution here. This is the step where you crank out a whole lot of algebra, hoping you arrive at something. And that something was this statement, 2 to the power of n plus 1. This tells us Pn is in fact true, because when we check out what the Pn statement is, we get the right structure, 2 to the power n plus 1. Now the whole proof is complete through strong induction, and look what it gives us. It gives us a way to compute here in method 1 all values of the sequence very, very rapidly, whereas out here, if for some weird reason you wanted the 330th term of the sequence, this is going to take quite some time. If you want, say, the 1000th term of the sequence, we might not be able to do that with the computation power we have whatsoever. So it's nice to be able to prove a nicer formula like the one down below over here. But the main takeaway from this was just understanding how the proof goes. Any questions at all, folks? Running through the full statements here. Okay, kind of a rough one to jump right back into right after spring break, but we're warming up. This was our warm-up to just rethink about how proof by strong induction goes. And now we'll try it once more on this final problem here, example 3. The so-called Fibonacci sequence. And this is great, but the Fibonacci sequence came from something applied in a real physical setting. They were looking into how population changes with rabbits when Fibonacci himself came up with this sequence. There is some debate on how to define the sequence. I should start off. Some people start with F0 as 1, or call it F1 as 1, and then the next term will be F2 as 1, and go on from there. Other people start at 0, then go on to the next, and so on. So this is our so-called Fibonacci sequence. Now, if we were to write out some terms of the Fibonacci sequence, just to get a feel for it, here's how it goes. F0 is defined to be 0. These are the initial values of the sequence. F1 defined to be 1. That's a comma down there. Then F2, here's where we take the recursive definition. It says take the prior value, Fn minus 1, that'd be F1, add the next prior value, that's Fn minus 2, so this would be F0. We come back over here, make the substitutions. This is 1 plus 0, and gives us just a 1. Really, all this is saying recursively is add the last two values together directly, not unlike the problem we just looked at. This is just a simpler linear combination this time. Likewise, if we do F3, we just take the two prior values. It'll be 1 plus 1, so we get a 2 out. Last one, F4 is going to take the value 2 plus 1 to get a 3 out, and so on. It eventually starts increasing quite rapidly, but it looks tame for a while. So that's our Fibonacci sequence. And this problem is going to go a little bit differently. Instead of discovering a formula for the nth term, which does take quite some work to write out and prove itself, we're just going to implement this sequence, working on the pseudocode directly itself. So this problem is more about focusing on the pseudocode. There's a related problem as well in the homework exercise. Let's start off by doing exactly that. We want to implement a function, so this will be our second time doing this kind of problem, returning the right term of the Fibonacci sequence, depending on what integer we provided. And we'll also execute it to see if it really works out. By programming language of your choice, it could be something basic like RStudio or Python, something more fancy like C++, maybe Fortran, COBOL, something crazy like that. But any kind of language should accept the pseudocode that we're writing with the adjustments that you would make, being the expert in the language that you pick. So this is kind of as well, not just a problem, but a demonstration as well at the same time. So let's start by saying, well, we're implementing a function. We need a name for it. You could call it just Fibonacci, Fibonacci underscore sequence. Anything built up like that would work just fine. But let's make this a little bit brief. Let's just call it Fib or Fibo. So I'll refer to the whole Fibonacci sequence as Fibo. So Fibo will get the result of a function. The input to the function is actually the subscript that you see here for visualizing as a sequence. All it's accepting is some integer n. So we'll write that as the parameter that gets passed to the function, just n. No error checking here, so we'll just hope that no one puts in a half and cause some weird overflow error, something like that. Curly brace is just going to say this whole block is going to describe the function. And, well, there's a lot of different things that happen with this, right? There's really three cases. There's the case you give the integer 0 passed to the function, integer 1, or the case you give the integer greater than or equal to 2. So one way to write this is by saying, if we're here, the integer provided to the function is 0, we can say if n, double equal says we're not making an assignment on n, but making a comparison. Compare that it's equal to 0. If this comes out as a true for a Boolean value, then we're going to return as an output to this function 0 itself, since that's the definition for the first term of the sequence. So that takes care of case 1. We just move over to case 2, case 3. Does that make sense to folks so far in writing out the pseudocode at the moment? Okay, let's move over to the next block then. For this condition, we can now say else if, or however this trichotomy would be handled in the specific language of your choice. I'll go with if, else if, and then just else to have the three conditions here. So let's say else if, we need to do another check, and the check is on the input to the function. It'll be n, do a comparison check to see if it's 1. If this check says true, then we return another value. The value being returned is going to be the output here on the sequence, 1. So far so good. Nothing too wild or fancy going on with it. But this is the big part. This is what gives us the actual recursive definition to the function, putting this in. So for the last thing, we'll just say else. We don't have to say n greater than or equal to 2 in any kind of way in the pseudo language, because that's already handled. You'll either execute here or here. And if it's here, it's automatically because n is greater than or equal to 2. So this is our final else. We need to capture this statement. But recall this should be the Fibonacci function, so Fibo, n minus 1. That's our hope if we define it correctly. This one should be Fibo n minus 2, and all we're doing is adding them together. So if we take that whole idea, this recursive aspect, we can say else, just return the Fibonacci function at n minus 1, so Fibo n minus 1. Notice it's calling back the original function right here, which again is always seems concerning, seems circular, but it truly is not. It's the same kind of exact recursion that you're seeing in right over here in its nature. So Fibonacci function n minus 1, add to it. Fibo for the Fibonacci function at input n minus 2. And we should be all set. Imagine if you did put in 2. If you put in 2, this is the Fibonacci function at 1. It's just going to return a 1 because it'll come back through this entire definition and execute right there. If n is 2, this is the Fibonacci function right at 0. And so right at this spot specifically, it's going to return 0 itself because the input to that function was 0. So we'll return a 1 here, a 0 there, adding them together when n is 2. That will absolutely give us f2, 0 plus 1, just as we did up here on our notes. So this should do the job for us. Let's close the entire function block. And then we'll do this part. Really, if this is a homework exercise, I can't directly ask you to do that. I mean, I could suggest it. This is really just you checking out if your pseudocode really works. And I encourage you to do so, just to get a feel for how this stuff goes. It's not a requirement, but just an extra check. Well, any questions at all, folks? Coming to the end of this function here. Okay, this is the exciting part of the problem then. We wrote down a bunch of stuff on paper. I mean, I know this is digital ink, but imagining we wrote a bunch of stuff down on paper. The question is, does this even work? So this will be our next step here. So in this particular programming language, R, we've mentioned this before, I'm pretty much just using the downloads that you can see here through the link on this. R is the computer program. RStudio is just the IDE that makes life a little bit easier, code completion, that kind of stuff. So now let's call this Fibo, exactly as before. Left arrow is a way to give a function assignment, so it just matches the equality right here. It'll be function n, and now we start putting in these 3 blocks in the middle. Let's see if we can space this out to really express them. So first, if n is identically 0, we return 0. Else if n is identically 1, return 1. Else, this should be our final condition, return the Fibonacci function at n minus 1 plus the Fibonacci function at n minus 2. So my claim is this should do the job. We'll see right away. So I'll hit Control A, Control Enter to just get this implemented. Now let's test this out. Fibonacci function at 0 gives us the 0 we're expecting. So far, so good. Let's check out these next values. Fibonacci at 1 gives us the 1 as expected. The second term of the Fibonacci sequence, this one, should be 1, and we do get the 1 out. So at this stage, it's starting to look good. Fibonacci at, say, 3 comes out as 2. At 4, we get the 3, and so on. Like before, there might be some challenges if we say, what is the 30th number in the Fibonacci sequence? This one could take some time. You might have saw the red dot right there, but here it is, 83,040. If we try to up that to 50, we might start to see some serious slowdown, and that's impressive. This is a pretty modern computer. There's a decent amount of RAM, but because this is a recursive function, the total number of function calls really at size 50 here is impressive. That's a decent math problem in its own right to say, how much computational power are we really asking here? Let's stop this one so that the whole environment doesn't get unstable as we're trying to present. But another problem we might have is, how do we know that that's right, really? That the Fibonacci at 30, that pseudocode implemented over here, really gave the right number. We'd have to just keep on executing this over and over again until we got to the Fibonacci sequence at 29 and 28, adding them together to see that this is really correct at 30. So like we mentioned before, if this was a bigger process, something that was mission critical to your organization, we can determine that this pseudocode really implements the Fibonacci function correctly by just running a couple outputs like this. I mean, we didn't even get this one to run at 50. We had to terminate that. So now we're doing the next thing. We want to prove that the pseudocode really implements the Fibonacci sequence at every single term, and we'll use strong induction to do that. So that's our tie-in with our last example to strong induction for part, I guess that should have been part B. Let's fix that part right there. Okay, let's grab strong induction as a statement as well, just because we're learning it. It's kind of nice to have a guide. And before we start, any questions at the moment, folks, with the pseudocode or our work on running it? Okay, let's launch into the proof then. Really, the first thing you want to do for something like this is do some work on saying what exactly you are proving. You're kind of setting a structure in your mind. You're doing a lot of the preliminary thinking before your hand starts writing. A lot of times, if this feels like a very vague, confusing problem, this is an excellent strategy just to get started. So if we're doing anything where we're proving something by induction, whether it's regular induction or strong induction, there's a predicate function in the background. So if you feel like these are pretty strange proofs, this is a good place to start. P of n is going to be a statement that, well, we're proving the pseudocode correctly returns the nth term of the Fibonacci sequence. And here's that pseudocode. So let's say P of n is the statement that the Fibonacci function at n returns Fn. This is the sequence, the Fibonacci sequence itself, and term defined recursively that way up here. So that's the predicate function. The statement that we're actually going to prove is the following. We will verify that for all n in Z greater than or equal to, a lot of my problems were greater than or equal to 1, but it is context sensitive. Sequence starts at 0 here, so we should say Z greater than or equal to integer 0, P of n. In the last section, I think we've mentioned this before, but it doesn't hurt to reiterate it. In the last section, we said that this is good enough, and it really is. That's the whole statement. It says for all n, in the integers starting at 0 and going higher, P of n it holds. But if you really want to emphasize that part, P of n holds as true, there's no harm in directly saying it right here. We're trying to show that the predicate function, that one, evaluates to true as an honest to goodness function for all integers n. So this is just a strong emphasis that often would get left out. So now we know exactly what we're proving. This part is just the proof. Let me zoom out just a touch. Here's our guidance down below on how to get through this. For the base case, we'll prove P of 0. But you know, this is context sensitive as well. Even our author mentions on our very first proof, I believe, for strong induction, often you want to prove a couple additional cases. Because our pseudocode has two special cases, when n is 0 and n is 1, those should be our base cases to verify in this kind of setting. So let's start here by saying proof, and let me be a little bit more descriptive, by strong induction. Step one is to start with the base cases. Not a bad idea to pluralize it. As just a reminder, we'll check out case n is 0, n is 1. So start by saying, let n be set equal to 0. We're over here on this Fibonacci returns fn part of the predicate statement. We're just trying to prove p of 0 is true. So we will say next. Then, to prove that we get true over here at p of 0, let's look at both sides. Think of the returns as just a way to say equals. Fibonacci at n is going to be, well, because we start at 0, we execute this block right here. So it executes the if block, only because we set n equal to 0 itself. And all that it will do then is return 0. So not much going on. So on the left-hand side, we're returning 0. But on the right-hand side, when we look at the terms of the Fibonacci sequence, first term is 0. So we can now say also f0 is 0 as well. We have a match. Something returns 0, the pseudocode. The actual first term of the Fibonacci sequence is 0 itself. We can write next, and so p of 0 is true. So one down, we now have infinitely many more integers to go, but only one more base case to check, the one where n is equal to 1. It's really just a rinse and repeat of what we said right here. We'll just say next. Let n equals 1. We go back, take a look at what happens with the pseudocode. Let's write then Fibo at 1 returns. We have to trace the syntax to see what happens. Sure, it's not overly complicated yet, but we're getting into some syntax already in chapter 7. We're tracing it through, starts to get more and more involved. So think of this as practice. If this doesn't seem too built up to you, we're building up something a little bit more impressive as we get further and further along. So tracing through, we set n equals to 1. We skip this block, but this block here will be executed only because of that comparison check. Boolean is switched to true here, and so we do that return. Let's say down below in our proof, the else if block executes, returning 1. Also, f, let me take another look at what I wrote. I was looking at this part here and this part here. I want to say also f1 equals 1. And so p of 1 equals true, or evaluates to true as a function. So we have what we wanted before. So a match on the output and the sequence. So the predicate function at 1 is true. But again, I'm noticing something weird on the way I wrote this out. I lost some parallelism. The Fibonacci sequence is written with a subscript to indicate the input. Here I actually wrote it out with honest mathematical notation. Should fix that notation just so we're not suddenly massively confusing the reader of all this, and write it out this way. f0 equals 0. I'm not super picky if you mix notations like that, but it is a good goal to not confuse a reader or yourself, because that looks a lot different suddenly by just keeping some parallelism throughout your syntax as you write. But we did it, folks. That's the base case. But once we maneuver through the inductive case, we'll be home free on this one. Any questions at all with the conclusion of step 1? Okay, now we're on to the fun part. We want to assume that p of 0, p of 1 are true, as well as all the way up to pn minus 1. We let n be 0 here, and we let n be 1. So in our next step, we'll say n is greater than or equal to 2. So this will go up by 1 right here. So let's say here, for the inductive case, or step, let me fix some of this a little bit. This is step 2 now, the inductive step. We will assume actually, before we assume anything, good idea to set the integer. Let's say first, let n be bigger than or equal to 2. Okay, that's important because that allows us to go up to this stage right here and to this stage right here by clearly saying what index n are we really using on our next portion. So let n be bigger or equal to 2 and assume that all of this stuff right here is true directly. So P of 0 and P of 1 and P of 2 and all the way through Pn minus 2 and Pn minus 1 is true. Huge assumption. But really, we only need a couple elements of this to complete our proof. Like a lot of the other proofs we've done in this section, we're going to need this case and this case when we go to complete this last portion. We want to show that the predicate function P of n itself is true. And recall P of n is just the statement. The Fibonacci function at n returns f of n. We can show that right there. We are home free. The entire inductive proof is over. Let's say that just in ordinary words. We must show Pn is true, meaning, well, P of n is true, then this statement here is a true one, meaning phi bo n returns Fn. So let's get started. The way we navigate through this blue part, showing that P of n is actually true, is highly similar to how we analyzed the base cases. So we're going to really start off in that kind of way. We already have the assumption, and it's greater than or equal to 2. So let's begin by saying phi bo n executes the else block right here. That's because n is not 0, n is not 1. We assumed greater than or equal to 2. We are down here executing this block. So let's say it executes the else block. If that block is executed, only one thing will happen. This is what the function will return back to the user, and returns these values, phi bo n minus 1, phi bo n minus 2. But when it returns those values, these statements down below are relevant to it. Pn minus 1 is the statement that phi bo n minus 1 returns the Fibonacci sequence at n minus 1. So that's pretty big information for us right here. And same with Pn minus 2. It says the Fibonacci function returns Fn minus 2. We'll directly use that information down below on our next step to say it returns phi bo n minus 1 plus phi bo n minus 2. Highlighting these parts in yellow as a reminder, those are the parts of the inductive step right there that are now relevant, because this is then equal to, or we could say returns right where the red dot is, more of a stylistic choice at this point. I'll leave that kind of judgment call up to you. For me, concluding the proof right here, I think equality makes a little bit more sense. So we'll say Fibonacci function n minus 1. Because Pn minus 1 is true, we get f. n minus one, the n minus one term of the Fibonacci sequence. Then add to it. Well, this is executed, Fibo n minus two, because the predicate function Pn minus two is true. Back up here, we return f n minus two. All we're doing is making changes to that subscript. So this is directly through the inductive hypothesis. The portions highlighted in yellow here after the step two. But once we have fn minus one plus fn minus two, we scroll up for just a moment. That's the definition for the nth term of the Fibonacci sequence itself. Just fn minus one plus fn minus two. So down below, we say that this is equal to fn. This is by the definition of the sequence itself on that last equality. And so finally, we can say when Fibo n is executed, what gets returned is the nth term of the Fibonacci sequence. That predicate statement at n has been shown to be true. That means we've shown it's true at every single integer n. The pseudocode will correctly return fn no matter what, is what we've said. We just need to finalize this proof. Let's see, what should we say? The Fibonacci block executes, returns fn. This shows Pn is true. How about to end this one, let's say, therefore, Pn holds. Recall Pn is just the statement, our pseudocode works correctly, essentially. It holds for all n greater than or equal to zero. We already said we're proving this by strong induction. It'd be kind of redundant to say a second time down below here, but no harm done if you did. So those are the steps for strong induction. It always looks and feels quite a lot different when we're proving our pseudocode actually executes correctly. But this is what the work looks like. A great use of actual induction, just like we did in section 5.2. Well, any last questions or comments, folks, concluding that final induction problem? Okay, it's attempting to save this. Let's hope it's successful. There it goes. I think it did get a good save on there. Well, congratulations, folks. I think this was the rough part of the course. Chapter 3 is fun, talking about logic. Quantifiers gets a little bit dicey, but it starts to make more sense the more we work with them. But I think for a lot of people, chapter 4 is intense, and chapter 5 is even more intense, but we've survived it. We're now moving into a more applied section of the textbook. Chapter 7, working with number theory, and specifically 7.2, we'll be looking into more issues with modular arithmetic. That's stuff we started with all the way back in section 2.2, where we introduced the mod function. So now we're going to finally do a little bit more with this and see what else new things we can do in chapter 7. Here's how it starts out. Starts out kind of light at first. We're doing some honest to goodness number theory with an eye for applications in computer science. So we'll be doing plenty of pseudocode along the lines, looking into algorithms in this chapter. And anytime we have an opportunity to play around with algorithm, we'll also implement it like we did over here, just to see how it works, test it out, that kind of stuff. It's a great way to just work with pseudocode and understand what are we trying to achieve when we write pseudocode in the first place. So here's how the brand new chapter starts out. It says for section 7.2 modular arithmetic, we're starting off with a definition about divisibility. But really, it's a huge callback to this good old function, n mod k. So that makes another show. Maybe just for the sake of a bit of a review on this, n mod k is just a remainder after dividing n by k. But really, there's so much more to say about that. This is a really, really tricky function. So our author also has an interesting way to compute it. N mod k can be computed this way. It's equal to n minus k times the floor of n divided by k. We'll have a lot more to say about this right here, but notice it extends the mod function to allow for n to be negative. We gave some answers on why having n negative is a reasonable thing to do, why computations are coming out correct, but it's hard to give a good and honest answer to that until you've got this right here. The division theorem, sometimes called the division algorithm, is going to give us a lot more clear information of what in the world is going on when we do this problem. This was an actual homework problem from section 2.2, and it was the most asked student question of all time for this course to date. So it will be a nice one to take a look into for the second time through the division algorithm, or the division theorem as our author calls it, to see what's really going on with this and give a more satisfying answer than what we attempted to give back in the day. We'll look into other interesting algorithms and processes, least common multiples, greatest common divisors. But think of this as, if we're doing number theory, these are some of the main components we want to discuss in number theory. Starts off with really issues of divisibility. And modular arithmetic is a big part of that now. Well, let's take a look at the definition. It says if we have two integers, k has to specifically be non-negative, and n, now that one's allowed to be any integer whatsoever. We write this. This is notation that was introduced a little bit in chapter 2. That's kind of been abandoned. We haven't used it a lot. We write k/n. We read this out by saying k divides n. And when we say k divides n, we mean it divides it evenly, and we get an integer. So let's say k divides n evenly. So that's a nice shortcut there. K divides n will just be k/n. It does feel awkward because when I see that, k over n, my brain wants to see it this way, k divided by n. That's the wrong thought. It's really n divided by k is what we're dealing with. So you have to resist the urge to think of that as a fraction bar whatsoever, because it can really make it seem a little bit different than what you really wanted to. It's not k over n, it's n over k, in other words. So k/n means k divides n. Saying it divides n evenly and the result is just an integer is expressed right here. N mod k is 0 means the remainder after division by k into n is 0 itself. That's an even division. It would mean k over n is an integer. So that 0 right there means k divided by n is in z, some integer now. And that's what we mean by divides evenly right here. And we can also say k divides n to mean it divides n evenly, or n is a multiple of k. This one's actually kind of tricky right here sometimes. This might feel like a lot of interesting review, but when words like divides and multiples and factors and divisors and quotients and remainders all are on the page at the same time, it's a good idea to kind of spend a little bit of time with this and just get a feel for the language. So k divides n, that's what we said right here. That's all k/n is really meaning. But n being a multiple of k, that deserves a little bit more of a description. So recall, k over n just means we're doing k divided by n, and it's in z. But that would mean k over n is in z, implies there exists an integer a in z such that k over n equals a. Then what can we do with this? K will be equal to n times a. I just took this last equation, cleared the denominator. That's what's being expressed right here. N is a multiple of k. It's the 8th multiple of k, because n times a equals k altogether. These are all totally synonymous statements, so it's a little bit disconcerting that this equation is encapsulated right here, which is encapsulated right here, and right here, and so on. It's really kind of a lot of stuff when you think about it. And our author mentions this is stuff that you've learned in elementary education, and that almost seems kind of wild in a way. That's a lot to put in one kid's head in one day, but this is over the course of years, you have to keep in mind. Last thing is that k is a factor of n. Let's see here. How can we get that out? Actually, I have a little bit of trouble with this one. If k is a factor of n, I would expect this statement to be rewritten out as k equals or n equals something else times k. So if k is a factor of n, then n would factor as one integer times another integer altogether. But notice I couldn't just take this equation and reuse a on that. I had to come up with another integer b to make some sense of it. Where would that integer b come from, I wonder? A little bit to think about on this one, it seems. But any questions at the moment, folks, while we're looking at that? Yeah, go ahead. Yeah, let me take a look at that. So you're referring to this spot right here? Gotcha. And that came from this statement pretty much. K divides n evenly. Oh no, you're right. That was a weird mistake I made there. That should have been, let me use a color that's going to make this pop out a little bit better. This should have been n divided by k, which corrects over here, n divided by k. I was just saying how this feels like a lot of stuff. And now with that correction, n divided by k, we're getting a little bit closer. That gives us an entire correction over here. N is going to be equal to a times k. N is a multiple of k. Let me think of that again. Yeah, it's the 8th multiple of k, so that still makes sense. And this is the part that was revealing to me a big problem in the work. K is a factor of n. It absolutely is. It's right there. We don't have to do anything contortionistic to actually see it. So the trouble was I had the fraction flipped. After saying, don't flip the fraction from right over here, I did exactly that. Thanks for spotting that one. But that corrects all these weird little issues. Does that make sense to folks on the part where we say k is a factor of n? Okay, so here's our start on number theory so far. We threw a whole bunch of concepts on the page all at once, and some honest work to separate out what's all going on there. So now, example one is just kind of a warm-up exercise. Looking into the definition above one more time, we have two propositions. This one says 21 divides 3. This one says 3 divides 21. We want to know which one is true. But if we take a look into these, we can probably eliminate one right away. Anyone see which one has got to be false in that list?
I would assume it's the 21 pipe 3 because you just said that the order is um the last one is divisible by the big one on the left. Is that correct?
Exactly, yeah. That was the
Okay.
problem right over here as well, is that I was looking at there and did it backwards, put K over N. 4 corrections on page now, but yeah, good call. This one right here says 21 divides 3 means 21, or excuse me, 3 over 21 is in Z. But that's not true at all. 3 over 21 is not an integer. It is not an element of Z. So this is false. It's a false proposition right away. This one is saying, or means, 21 or 3 divides 21 means 3 goes into the denominator so that it can divide 21. I think the base safety here is just to say it out loud each time you see it, then visualize it as a fraction. 3 divides 21. If it divides 21, that means the output to that is an element of z. And it certainly is. It just results in a 7, definitely in a set of integers. So this one is true. Well, that's the big takeaway on that. This is kind of a complicated structure to take a look at, but it makes sense if you read it out each and every time you look at it. We're going to be doing a lot with modular arithmetic, but n mod k is the remainder after division by k. So we're looking into divisibility itself right here specifically before we get too far along. Let me just fix that box there so it's not too busy. Next, as far as divisibility goes, loads of awesome theorems. Here's a whole bunch right here. Let's maybe put this on the next page. So thinking about what these are saying, it's saying a divides 0. And, that's certainly true because it's saying a over 0 is 0. But notice what's not said there. This is a false statement if a itself is 0. So it's assuming immediately, provided, oh, that causes a crash, I remember now. This is provided a itself is not equal to 0. Our author didn't say that, but in this part of the book, I think what the author is trying to get us to do is think in terms of what are the domains of each of these things as he puts them down relative to each one of these statements down below. It's kind of a way of proofreading as you write. This was meant to be an assumption that we had to put in ourselves as we read through this statement here. So it's coming from this, just a new way to denote it. Next one says 1 divides a, and this one doesn't have any special cases. It would just be 1 divides a, certainly true. It's always equal to a itself. A is meant to be an integer. A divides a, certainly true. That's just putting down a over a equals a. Oh, equals 1, thank you. A over a equals 1 itself. That's some bad arithmetic. That would have only been true in one case, but now it's true always. Thank you for solving that one. And then last couple are more interesting properties. This one says if a divides b and b divides c, you get that a divides c. This property is actually fantastic in a way. This is called the transitivity property. Oh dear. The transitivity property. What's nice about transitivity as a property is it's something that we use all of the time, essentially. It's an honest to goodness algebraic structure, and it's encouraging to see a property like this show up in divisibility. It's saying if a divides b, but then b divides c, then a itself divides c as well. The way we usually use transitivity is we might say maybe about x equals 5a, 5a equals 2. By transitivity of equality itself, you would say x equals 2. The 5a is just the intermediate middleman to connect the far left side x with the far right side 2. And the same thing is happening over here. You have divisibility a into b, but b divides c. A itself has to divide c as well. So it's kind of a nice property to have. There's other interesting properties to mention here. This might be considered a symmetry. This might be considered anti-symmetry. And this is a kind of distributive property in a certain sense. But these are the kind of major one I wanted to highlight, the transitivity property itself. This property is actually kind of amazing in a certain sense. I need to bring that part back. But if you visualize this, we've seen this itself as well as an algebraic structure. A divided by b, or excuse me, a divides b, and b divides a implies a equals b. Well, not exactly. If a is allowed to be any integer, then it's either a is b or a is negative b. The way we've seen this part before is we said if a is a subset of b and b is a subset of a, then a equals b itself. That's going up to this part. But there's a slight extension, kind of annoyingly. If a is allowed to be any integer, it doesn't quite follow the structure. A could also be equal to negative b at the same time. But anytime you can find a connection, it's worth thinking about it, because these are really just algebraic properties that could extend to some other algebraic system. Finally, the type of distributive law says if a divides b, a divides c, it must divide the sum of b and c. I think this one feels intuitive to folks. So that'll be our first one we prove on this list right here. I have just one proof like this on the homework assignment itself. You can come back here to example 2 to see what would this proof strategy really look like. But I think you'll like it. It's kind of similar to the proofs that we did all the way back in chapter 4. We won't be doing a lot of proofs like these, but it's not bad to take a couple times when we see a big theorem like this to prove a couple cases. Any questions at all, folks, about the theorem before we go and take a look into that last statement there? Okay, let's give a proof then. So a divided by b and a divides c implies a divides b plus c. If we were to rewrite this in its a slightly different logical structure, it would be like this. Prove a divides b and a divides c implies a divides b plus c. So this is the logical structure of what we're about to prove, which means we're proving an implication. And whenever we go to prove an implication, first step is to assume that part's true. We use that information to conclude that part's true. So that's how we're going to connect all this together. And now we're ready to start. So with our proof, immediately assume this part is true. And these are really assuming two things, a divides b and a divides c. Let's say right away, assume a divides b and a divides c. Off to a good start. Once we write that down, we want to immediately say, what does that mean specifically? This means starting on this one, a divided by b, there exists some integer, let's call it, we can make it k. The k plays a lot of different roles in these notes, so k could be pretty distracting. We could make it m or n, but those come up a lot as well. How about, let's go for w and u. Those are inoffensive symbols that won't conflict with anything else on these notes. So it's playing the role of like when we said there exists k, x equals 2k for even, for example. Let's go with there exists u in z such that a divides b. So a divides into b that way. That's just for safety, writing it in that way. Means it equals an integer u in z. We quantify it first. There's the equation. And let's just do it again for this part. If a divides c, there exists an integer w in z such that a divided into c equals that integer w. So now we have a couple equations that we're going to work into. We want to show a divides b plus c directly, but let's first start with the equations down here and figure out what we can do to manipulate them. So next step to take. Well, we could solve for b right away on this. We could write that from this part, b equals au. Let's do the same analogous thing. From this part, we could solve for c. C equals AW. And this is our target up here. We want A to divide into B plus C evenly. But notice we have a way to write out B and C all at the same time. So let's see what we can do with this direction. Therefore, A divided into, so now I'm using just actual honest division, B plus C is going to be equal to, by substitution, B is AU from over here, plus another substitution, C is AW. We're dividing this all by A. But that looks fantastic. We have a greatest common factor of A in the numerator, so we can factor it out, cancel A right here. Or if you like, you could divide right now. Let me take the extra step. We get U plus W after the cancellation right here. You know, getting U plus W really isn't good enough. There's one extra statement that we have to make. Because depending on what happened with the algebra, maybe you had U plus W over 3. That's highly, highly concerning. Because on the right-hand side, it may not be an integer if you've divided it by 3. If you did something like this, though, no problem at all, because if U and W is an integer, the square of that's an integer. But if something weird happened algebraically and you were tempted to take a square root, big problem again. U plus W has to be a perfect square, or else it's no longer an integer. But notice what we said about U and W. We said U is an integer right here. W is an integer, and adding two integers together just gives you a whole new integer. It's in Z, deserving an exclamation mark because that was a major thing we want to show at that step. If we divide A into B plus C, we get an integer, and that's just another way to say this statement. Therefore, A divides B plus C as required. That completes the proof. So that's what a division type of argument would look like. Notice it really isn't too different than what we did all the way back in chapter 3 when we were proving weird facts about even integers versus odd integers or divisibility properties. We're really just using those same kind of arguments, adapting it to what is new notation that we're facing. Well, any questions at all, folks, on this one here? Okay, looking at the clock, I don't know if I have enough time to give an honest introduction to the next part, the division theorem. This is a major key to these notes right here, and I'd hate to break this last problem in half. So what I propose is, let's do a part B to this one. That'll support the homework question as well, where we have to prove one of these properties as well. So let's make this part B, and let's prove this one. We made a big deal out of it, so we might as well go for the transitivity property. I believe the one that you're going for in the homework is not quite on this list. It's a brand new property, not on here, but strategies on part A and the one we're about to list down on part B will be highly similar to help out. So new statement to prove, let's let it be this one. No longer the final statement, it's just this statement right here. So A divided by B and B divided by C implies A divides C. Instead of adding new logic notation to it, I think there's plenty of notation already added in. Let's jump right into the proof. It's kind of nice that it's not an induction proof, so we do get a bit of a break here on that. We have an implication connected through an and, or excuse me, we have a conjunction here with two parts. Then we have an implication where we have to show A divides C. But because the left-hand side, the hypothesis, has the and statement, the conjunction, that's good. That means we assume two pieces of information. We start by assuming A divides B and that B divides C. So let's say that right away. Assume A divides B and B divides C. We must show A divides C itself. If we can show that, we've shown transitivity in the same exact algebraic sense as transitivity of ordinary equality that we've been using since as long as we can remember, probably. Well, we begin with the assumptions we made and just push forward through those. A divided by B means there exists an integer, I'll go with U's and W's again to avoid notation conflicts. There exists an integer U, so U and Z, such that A divides into B, resulting in U. So that's the A divides B part. This one's a little bit different because now A is gone from this statement here. So this proof is a little bit different than the one in part A. B divides C means there exists. Again, I'm a little bit rusty with this tool today. Sorry about the weird glitches. There exists W and Z such that, let's take a look at it again, B divides into C, resulting in the new integer W just quantified. We have to show A divides C using this information, but this gets us started. Now, the strategy that worked really well from us before was clearing the denominators so that we're not looking at the division equation, we're looking at a factorization equation. So we can write out from here, this implies B equals A times U. Then we do it again, and C equals B times W. C is the main star of the show at this part of the proof because we want to show, to finish this off, A is going to divide into C evenly. So let's show that. A divides into C evenly. Hard to argue our way through this unless we start doing the major algebraic tool that's been working for us all along in these proofs. We just do a substitution. Right where that C was, grab this assumption. C is B times W. It's being divided by A, but we're still stuck right here. There's no A in sight. However, we use that strategy again, because if we have a B here, B is just A times U. We can throw that in. So on the next step, this is equal to A times U, just a new substitution. I'm running out of color, so I'm using the box here as a way to highlight. Divide by A. At this stage, however, it is very clear A divides C because A is a factor of C. It shows up right here. It cleanly cancels out, and we just get, excuse me, U times W. But we never celebrate early right here. We have to consider, what are we doing with U and W? We're purely just multiplying them together. And it is true, if you start with the integer and a different integer, multiply them together, you get an integer again. This is in Z. Therefore, what have we shown? When we divide A into C, we get an integer. That's just what this statement way up here, the new notation is trying to say. A divided into C evenly. That's all we had to show. The proof is complete at that step. We showed what we must show, and so we can end it right here. So those are interesting divisibility kind of arguments that we're writing down. Nothing too different than what we've done in the prior sections. Maybe slight adjustments where when you get these equations, you make some adjustments and some substitutions to show the divisibility. I would say the major struggle with this new material is just getting that new notation in our head right so we don't get the fraction flipped. Again, the mistake I made at the start of class was, if I say see A divided by C here, my brain thinks A divided by C like that. That's not what we're doing. That's A over C. When we really need from this, C over A. kind of unfortunate notation when you think about it, but it's set in stone. We can't change it. We just have to live with it. Any last questions at all, folks, before we call it a day officially? Okay. Oh, sorry. Yes, go ahead. Yeah, absolutely. Let me pull those up next. Well, that looks like that's all I have for folks today. Kind of a shorter day. We're ending about 5 minutes early. But we're coming back doing induction, so I think this was a good stopping point for us. Have a great night, folks. I'll see you all in Wednesday's class. We'll just continue to push through section 7.2.